Good morning everyone. In this video, we are going to see about modeling and simulation of multipath fading channel, Rayleigh fading channel using Matlab. So before going to the simulation part, first you should know what is meant by fading in wireless communication. Let us assume you are going to a shop and you are buying a cloth which is red in color, pure dark red in color. After so many times of usage or after exposing the cloth to the sunlight, what will you observe is that the color of the cloth gets faded, right? Similarly, in wireless communication, when the signal travels from the transmitter to the receiver, the signal strength gets weakened. Why? Because there are several obstacles are present in between the transmitter and the receiver, which makes the signal strength to get weakened. So this is said to be fading in wireless communication. So fading is the variation in the amplitude, phase or power of the received signal. So which is caused by reflection, diffraction, scattering and multipath propagation of the signal. Two important fading models are considered in wireless communication. One is Rayleigh fading and the other one is Rician fading. So this fading causes random variations in the received signal and it increases the number of bit errors. So next is Rayleigh versus Rician fading. So how to model or how to design the channel is based on when the direct line of sight path exists or not. When there is no direct line of sight path exists between the transmitter and the receiver, then the received signal may consist only of the signals due to scattered or diffracted or reflected components. So at that time, the channel is modeled using Rayleigh fading model. Second case is when there is a strong direct line of sight path exists between the transmitter and the receiver in addition to the scattered multipath components, then the channel has to be modeled using Rician fading model. So here I am going to consider BPSK modulation, binary phase shift keying modulation, where the binary zeros and ones are mapped as -1 and +1. That is, it uses two phase states that is separated by 180 degree. And here we are going to calculate the bit error rate by using the formula number of error bits to the total number of transmitted bits. So the ratio between the two gives the bit error rate BER. And then after calculating the BER, I am going to plot this BER with respect to my EB by N0 value, that is bit energy, to the noise power spectral density value, that is N0 in decibels. So now I am going to simulate this using Matlab. For that I am considering capital N number of bits, that is 10 power number of 6 bits I am going to consider. These 10 power 6 bits are randomly generated using this command rand of 1 comma n, which is a vector of size 1 cross n. So it generates random values between 0 and 1. If my value is less than 0.5 means that is assumed as 0, and if my value is greater than 0.5 means it is assumed to be 1. So randomly it generates binary ones and zeros. Now I am going to map these ones and zeros with respect to BPSK modulation by using this command 2D-1. So this, for example, let us consider substitute for D is equal to 0 in this formula. What you will get? 2 into 0 is 0. Minus 1. So my answer will be -1. Okay. Now consider the value of D as +1. So what is 2 into 1? That is 1. Minus 1 is 0. So, sorry, minus 1 is 1. 2 minus 1 is 1. So I have mapped the values of zeros and ones into -1 and +1 by using this BPSK scheme. Okay. Next, I am initializing the EBN0 value in decibels, that is from -5 to 20 in steps of 2 decibels. Then I have to generate an empty vector of size 1 cross length of EB by N naught. So I am generating an empty vector which consists of all the values as zeros. So this vector size is 1 cross length of EB by N naught. Okay. Next I am initializing the loop. So this for loop will run for length of EB N naught times. That much number of times this loop will be running. So next I have to generate the noise, which is a complex noise. So here it consists of real part as well as imaginary part, that is I. Okay. So next I have to define what is my channel impulse response, that is H, which also consists of the real part as well as the imaginary part. So that also I am generating by using, that is in a random manner. So next is scaling of the noise. By using this command, I am scaling the noise, that is converting into a linear scale by taking anti-log. 10 power in the sense it takes anti-log value and then multiplying with the noise that is stored in this variable n. So next I have to generate the received signal, calculate the received signal. So received signal is generated using product of channel impulse response with the transmitted signal plus the noise, that is n. So x into h plus n, that gives you a received signal. So next I am going to equalize this received signal by dividing the received signal with the channel impulse response h. So that value was stored in this Rayleigh underscore cap. So next what I am going to do is I am going to consider the real part alone. Right? Why? Because initially we have transmitted only ones and zeros, which consists of real part only. But here the channel impulse response as well as the noise consists of imaginary terms. So my received signal also may consist of imaginary term. So I have to eliminate those imaginary term. So for that I am going to consider real of this received signal greater than 0. So what are the values of greater than 0 which are considered to be the real parts? That value will be stored in this R underscore Rayleigh, this variable. So next I am going to find out how many number of bits are received with errors. Number of errored bits, that is calculated by using this XOR operation. So you all know about the XOR operation, that is if both the bits are same means my result is 0. If any one bit is different means my result will be 1, which means this XOR operation will compare the transmitted bit with the received bit. If both are same means error will be 0. If any one is different means error will be 1. So the count will be incremented, that is the sum value. It calculates the sum of all the errored bits by means of this XOR operation, right? So next I am going to calculate the BER value. So bit error rate is calculated by the ratio of number of error bits divided by total number of transmitted bits. So here I have calculated BER. Next I am converting EB0 value to a linear scale. I have initialized as decibel values. Now I am converting it into a linear scale, that is by taking anti-log 10 power value. This gives anti-log of EB0 value. So next is calculation of theoretical value of this Rayleigh model. By using this formula, I have calculated the theoretical value. Then I am going to plot both the theoretical value as well as the simulated value, and then I am going to compare both by using this semi-log plot. So why I am using this semi-log plot is that I have used many number of bits, transmitted bits. I have considered n number of transmitted bits, 10 power 6, which is more. So for that I am considering this semi-log plot. We cannot plot this in a linear scale, right? So this semi-log, this is used to plot the simulated value, and this command is used for plotting the theoretical value. Then I am defining the axis. Both x-axis and y-axis are defined in this command. I am defining my legend value. I have given the title for my figure. I have defined the x label as well as y label. So now I am going to run the simulation. So here see the plot. This green color plot shows the simulated values and the black color circles indicate the theoretical values. So both are overlapping, which means both are almost the same, right? Both are almost the same, which is the plot of EBN0 versus BER. So in this video, you have learned about the modeling and simulation of Rayleigh fading channel. So we will see in the next video. Thank you.